Assalamu alaikum and greetings. My name is Muhammad Sofi bin Shalazizi, and today, me and my group are going to be presenting our project that we have undergone the entire semester, which is the NDT inspection air compressor tank analysis. To start, let me introduce our project. This project focuses on the non-destructive testing of a decommissioned air compressor tank over at UTEM. As you all may know, NDT is vital for ensuring safety and structural integrity without damaging the material. We utilize a combination of three industry standard techniques to evaluate both surface braking and internal conditions of the pressure vessel. As with any other project, the reason that we are doing this project is due to the problems that are stated below. Number one being the operational history of the pressure vessel. The vessel has been subjected to cyclic pressure and environmental moisture for over 10 to 15 years, leading to potential degradation. Next being structural risk. Signs of active surface rust and minor dents on the vessel suggest possible internal corrosion or stress cracking. And finally, is limited access. The tank was not cleaned internally and access is restricted, making standard internal visual examinations basically impossible. In simple terms, the objective for our project is to assess the wall thickness and detect thinning due to corrosion and to identify surface cracks and weld defects that are critical at the joints. And next being to evaluate joints and connection points for structural integrity. And finally is to determine the serviceability of the vessel for future use. There are various NDT methods that are used in the industry, but for this project, we are only using three. Number one being visual test, which is going to be the initial assessments to identify obvious surface defects, corrosion, and weld discontinuities. And secondly, we are going to be using the ultrasonic test, which is going to be used to detect subsurface defects and measure precise wall thickness across the entire mapped grid. And finally, we are going to be using penetrant testing, which would then reveal surface breaking flaws like cracks or porosity that are invisible to the naked eye.
Assalamualaikum. My name is Mohammed Hakim, and today I'll be presenting the ultrasonic testing, or UT. Ultrasonic testing is a cornerstone of the modern non-destructive testing. This method uses a high-frequency sound wave, typically between zero point 0.1 and 15 megahertz, to see through solid materials. By analyzing how this wave reflects off internal boundaries, we can precisely evaluate wall thickness and detect hidden flaws without damaging the assets. UT is indispensable for assessing the structural health of critical components like storage tank, where internal corrosions can often hide behind a perfectly intact exterior. To maintain the highest level of accuracy, we rely on a specialized technical stack. Our primary instrument is the Crockramer USM36. It's built for the field with the IP66 ruggedized rating and a large, high-resolution screen that remains readable even in direct sunlight. We utilize a 12 mm dual-element probe. We are running at 4 MHz, which is specifically optimized for measuring wall thickness in corrosive environments. We also use a V1 calibration blocks and couplants to ensure the transducer maintains the seamless contact with the metal surface for error-free readings. Our workflow is divided into three phases. First is prep, where we clean the target surface to bare metal and mark a 250 by 250 mm grid. Second is measurement, where we systematically record data at 36 specific grid points. This is just about the single numbers. It's about mapping the entire surface to identify pattern of wear. Finally, we move to documenting, where every data point is recorded on a standardized evaluation sheet. This creates a reliable data trail that allows us to compare current reading against historical baseline. Looking at our final analysis, the data confirms a high level of structural integrity. Across the 36-point grid, our peak thickness reached 9.07 millimeters, which aligned perfectly with the tank original 9 millimeters nominal specifications. While we note somewhere the lowest recorded thickness was 5.86 millimeters, observed at coordinates 5, 20, and 29. Crucially, this thinning is uniform and minor, remaining well above the critical safety threshold. Based on this result, the shell is confirmed to be in satisfactory condition and safe for continuous service.
Assalamualaikum warahmatullahi wabarakatuh. My name is Habibur Rahman bin Hassan. So today I will present for this slide. So this is a penetrant testing. It's a liquid penetrant testing. It's used to locate surface breaking flow. It's non-porous material or capillary action. So for the methodology, it's a penetrant seep into flow, and then we surplus remove, and then we developer apply, and then extract the liquid blotting out for visibility. So let's check it out. So this is the equipment used for PT. So the first one is a cleaner, the second one is penetrant, and the third one is developer. So the first one, the cleaner, is used to remove the dust or the oil before we put the penetrant, and then after we put the penetrant, we put the developer so we can see the kecacatan in that equipment. So this is the PT workflow process. So the preparation, you need to surface cleaning using a cut brush to remove the old paint. After you remove it, we use a solvent remover to remove the dust or the oil. After that, we use a penetrant application. You can spray on the penetrant into the material well, and then for the dwell time is for 15 seconds for the 15 minutes, uh, and then after that go to the inspection. That after we put developer to see the uh, kecacatan in the equipment. So that's all. After the PT working flow process, we go to the PT data analysis and finding. After we do the PT to material tank, so this is our data that we found in equipment, that we found undercut, we found leg length, uh, a little bit location, mechanical damage. So that's all for me. Thank you.
Hi, my name is Faik Nabil Ashraf bin Fidaus Ilham, and I'm going to be presenting about our discussion. We can break our finding down into three key takeaways. First, the volumetric integrity is satisfactory because our ultrasonic testing confirmed that the main tank shell is still in great shape, maintaining a healthy and uniform wall thickness between 5.86 mm and 9.07 mm, with no sign of critical thinning. Second, we found rejectable weld defect. Even though the shell is strong, our visual penetrant and testing exposed serious surface flaws on the joint, including deep undercut, surface porosity, and bad leg length that fail standard safety codes. Finally, this shows why complementary testing is vital. If we had only checked the base metal with UT, we only have completely missed the defect, high stress weld joint. Combining surface and volumetric method was essential to get full safety. To wrap up our presentation, here is our conclusion. The pressure vessel itself still retains an adequate and safe wall thickness. However, it is not ready to future use just yet. The weld joint required immediately repair because surface porosity and undercut we detected exceed strict safety limit of the C-sweep Group A criteria. And once those joints are properly repaired and retested, the tank integrity can be re-evaluated. That is all from us. Thank you so much.